Hello everyone, my name is Xuelin. I am a PhD student from UT San Antonio. Today I'm going to talk about our work, ConDySTA, Context-Aware Dynamic Supplement to Static Taint Analysis. Taint analysis is a data flow analysis technique which has been widely used in security domain, especially for detecting privacy leak. It can be used to track how private information flows through the program and check if it flows to some untrusted places. A taint analysis tracks data from predefined data source to predefined data sink and aims at discovering the data flow between sources and sinks. Well, a source is a resource where the data is accessed. It could be some device resources like location, device identifiers, or some data from users' input like email address or password. And a sink is where the data will be written to, like a local file or text message. This is an example from an Android application where at line 5 we have the source data, where the program gets users' password from the GUI input box, where the user might input their password when they try to log in. And then the password is saved in a string, and then this password string has been saved into object user. Under the second method, send message, which is a callback method, it can be triggered when the user maybe click the button on the screen. And then the program will get the password and put each character to another string called obfuscated password. And this obfuscated password was put into another string called message. And finally, this message will be sent out through the API send text message at line 24. And this is the sync point, where the password will be sent out through text message. Well, by looking at this code snippet, we can tell there might be a data flow from the user's input password to the API sent message. A static taint analysis tool is able to detect such data leak by tracing the data flow from source to sink. Static taint analysis is supposed to be conservative because it propagates taints on all possible program paths, leading to the detection of all possible taint flows with some false positives due to invisible paths. Back to this example, static analyzer will consider this data flow as a password leak. However, if the callback method send message will never be triggered during runtime, if it is an invisible execution path, then the password leak will be a false positive. While in security and the privacy domain, it is a well-known problem that the static true analysis often produce false positive. Sometimes it's acceptable because we don't want to miss any potential leaks. However, false negative also exists in static taint analysis and often being neglected due to the impression that static analysis is always conservative. Actually, in the real-world applications, complicated and heterogeneous code design often lead to false negatives in static taint analysis. These false negatives can come from the interaction with third-party services. When the data is sent to a third-party service, the static analyzer will lose the tracing. The false negatives can also come from dynamic loaded code, where the static analyzer does not have any access to. Those are kind of like a black box code for the static analyzer. Okay, let's take a look at one example of false negative. On the left, we have the source data at line 6, and then this source is saved in a variable called in. And then at line 7, we call the method foo and use in as an argument. And inside the method foo, at line 2, we just assign in to out, and then return out back to line 7. And then at line 8, the out has been passed to the sync point. This data flow is pretty simple and straightforward. The static analyzer can detect such data flow from source to sink. However, if we have a different definition of foo, where the variable in was sent to a third-party server, where we don't have any access to their code. At this point, the static analyzer cannot trace this data anymore. And later, when the data comes back from the server, static analyzer won't be able to tell whether this is a taint value or not, because we already lost the tracing of that data. In this case, a static analyzer will miss this data flow and have false negative due to the inaccessible code in the remote server. So we are trying to reduce such false negatives by identifying the missing traces through dynamic analysis. Basically, we check the data returned from the inaccessible code and check whether it is sensitive or not. If the return data is the sensitive data, then we consider it as an intermediate source and apply the intermediate source on the static taint analysis. So back to the previous example, we will check whether the return value from the server is sensitive or not. If it is sensitive data, we will consider the method foo as an intermediate source and apply static taint analysis on it to see if it flows to a sync point. By doing this, we could detect the missing data flow. So that's our idea. And in our design, there are two major components. Dynamic analysis, where we perform GUI testing to check the return value from the inaccessible code and identify the intermediate sources. And static analysis is where we apply static taint analysis on the intermediate sources. In the first step, when we perform dynamic analysis to collect the intermediate source, we instrumented all the methods whose return types are string. After instrumentation, we rebuilt this molecule back into APK format for testing. We use the Android debug bridge to automatically install the rebuilt apps onto our test device. And then we use the predefined user profile to perform the testing. And we let the monkey to explore the apps for 20 seconds. So monkey is a popular GUI testing tool that generates random user events on the Android application. And during testing, we utilize the Android system log to record the return values and the call stacks of the string type method. When a method returns a value contains any user data that we defined in the user profile, we consider that method as an intermediate source. After identifying the intermediate sources, we apply it on FlowJoy to detect additional taint flows. Then we found there's a problem in ConDySTA, that is, we didn't consider the context of the intermediate source. Under different contexts, a same method can return different values. It could be sensitive or non-sensitive. Let's look at this control flow graph for a simple program where we have three methods. For the first method, bar, in line 1 we get the taint source. And in line 2, we call the method foo with the taint source. And then inside foo, we call blocker. Let's assume that the blocker will send the source to a remote server that we don't have any access. And then it calls for true. And inside for true, we get the data from the remote server through blocker 2, and then return this data. Our approach, ConDySTA, will identify this is a sensitive data and consider it as an intermediate source. Then this source will return back to the method foo, and then back to the method bar. Finally, in the method bar at line 3, the source will pass to the sync point, and ConDySTA will identify this data flow and consider it as a leak. But later, when we have a non-sensitive value called safe, and then we use it to call foo, and then call foo2 as what we did in the previous code, and then return this safe back to line 5 in the variable called out2. And then the out2 will flow to the sync point at line 6. Since we consider foo2 as a source, our framework ConDySTA will detect this second flow as a leak, which is a false positive, right? Because the foo here is just returning a non-sensitive data called safe. The reason for this false positive is that when we applied the intermediate source to static analysis, we didn't consider its context. So when the intern here becomes the source, It will flow back to both line 2 and line 5. So we need to add the context information for the intermediate source. In this example, only when the source is under the red context, it is a valid source. When it is under the green context, it is not a valid source. So we need to inject calling context into our approach, and we call this framework as ConDySTA. In order to add context information, ConDySTA takes advantage of a key observation that the static calling context of an intermediate source is always a subsequence of the call stack trees. In order to match the static calling context with the stack trees, we converted the dynamic call stack trees into a calling context like this. For each invocation in the stack trees, we extracted the caller and the callee and also the line number, and then use this extracted calling context to compare with the static calling context from FlowJoy. If those two contexts match, we consider that as a valid leak. To evaluate the effectiveness of ConDySTA on detecting additional taint flows, we applied ConDySTA on the apps from RepoJoy. So RepoJoy is a comprehensive benchmark framework for Android analysis tools. The benchmark apps covered code features include implicit taint flows, native code, reflection, and intercomponent communication. We applied ConDySTA on RepoJoy, and it detected 12 taint flows which were not detected by any of the 6 state-of-the-art static taint analysis tools that included in the RepoJoy. The table shows the details of these 12 taint flows. In flow 124, the source data has been converted into an array of char and copied back to another stream before flows to the sink. In flow 191 and 192, native code were used to fulfill part of the taint flow. In flow 203 and 206 to 209, part of the taint flows is fulfilled with the method invocation performed at reflection, along with dynamic generation of class or method signatures used in reflection. In flow 24, 25, 27, and 32, the data is transmitted across components through intents. ConDySTA detected these 12 flows based on intermediate sources such as the method called copy IMEI from the app implicit flow 1 and the method called getStringExtra from Android content the intent. To evaluate ConDySTA's performance on reducing false positives caused by context insensitivity, we applied both DySTA and ConDySTA on 43 apps from RepoJoy that contained at least one true negative. Among the 186 true negative data flows, DySTA mistakenly reported 9 of them, which are false positive. And then with context matching, ConDySTA did not report any of them, so ConDySTA reduced 9 false positives from DySTA to 0. We further applied ConDySTA on 100 popular Android apps from Google Play. On top of FlowJoy, ConDySTA was able to detect 39 additional taint flows from 12 apps. Some taint flows that were detected by ConDySTA but missed by FlowJoy because the data were sent to a remote server and come back later, or the data was flowed to a local cache files and later the data was read back. So the evaluation result shows ConDySTA was able to handle different types of inaccessible code in the real-world application, and also the idea of using dynamic analysis to reduce false negatives in static analysis is promising. Our work presents the following contributions. We first demonstrated that dynamic taint analysis results can be used as a supplement to static taint analysis to reduce false negatives in practice. We developed a novel approach, ConDySTA, to preserve the context sensitivity of the taint analysis. We performed the evaluation using the RepoJoy benchmark and also 100 popular Android apps from Google Play Store, and our evaluation result demonstrates that ConDySTA can reduce many false negatives reported by the state-of-the-art taint analysis tools. More details about this work can be found in our paper.